Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows of ISAR Berhampur. So I am the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pan from IIT Guwahati. In this session I usually discuss about some questions based on this chapter, that is Reagents in Organic Synthesis, which may help you to solve your assignments and also the upcoming examination. Till now we have discussed about oxidation, reduction and some reagents. So today we will discuss some transition metal reagents. So today we will discuss about reagents containing different transition metals. So there are various transition metal containing reagents are there: tin, lead, bismuth, titanium, ruthenium, palladium, copper, chromium, manganese, zinc and many of them. So today we will discuss some of the transition metal containing reagents which are important from the perspective of your examinations and your assignments. So today we will discuss about reagents containing tin, lead, titanium and zinc. In the next class we will try to focus on the other, mainly the palladium and copper, which are very important for your organic chemistry because they are widely used in different type of reactions. So in the next class we will discuss those. For today we will discuss about tin, lead, titanium and zinc containing reagents. So the first is zinc containing reagents. So organozinc compounds are prepared from alpha halo esters in same manner as Grignard reagent. This reaction is possible due to the stability of esters against organozinc and due to the very low basicity of zinc enolates. There is hardly any competition from proton transfer and the scope of carbonyl addition partners is quite broad. In presence of ketones or aldehyde, these organozinc compounds react as a nucleophilic partner in addition to them to give a beta hydroxy esters. So if you see the reaction, here we are taking an alpha bromo ester. If you add zinc inside it, what will happen? It will form a zinc bromo ester, that is zinc will incorporate inside this CBr bond, forming a organozinc compound. Then when we add a carbonyl compound into it, this carbon become partially negative charge due to incorporation of zinc. Now so this attack to this carbonyl center and give us a beta hydroxy alcohol. Why beta? Because this position is alpha with respect to carbonyl and this position is beta. So we get a beta hydroxy ester. So this can be applied specifically for alpha bromo esters. If you add a ketone inside it, this type of reaction usually don't perform. So this is specifically limited for alpha bromo esters, only for esters, due to stability of this zinc bromo organozinc reagent. If it is a carbonyl compound, this type of stabilization will not be achieved. So the zinc can be also used as a reducing agent. In our plus 2 we have also read about this. If you add zinc HCl into nitrobenzene, what will happen? It undergoes a reduction, forming a aniline. So NO2 can be easily reduced to aniline in presence of zinc. based on this zinc, one question came in previous GATE examination. So if you add zinc and this aldehyde into this type of alpha bromo ester, what will happen? So let's go step by step. After addition of zinc, what will first thing will form? It will form a alpha bromo zinc ester. So this zinc will be incorporated into the CBr bond, forming this because this carbon becomes partially negatively charged. So this would attack this aldehyde carbon. Forming this now there is a OH group and there is a ester, so it undergoes a trans esterification. There is another question based on Grignard test. So please try to solve this one. So in the first step, we have the correct option is option C. Reduced ester to alcohol. The correct option is option C. So if you add one molecule of dival H, just consider this as a H minus. This one will attack here and it will open up. Let's go to the next question. So if you add, so this is also from a previous year GATE examination. So if you add this orthonitrotoluene and this diester compound, what will happen? So let's go step by step. So there is a methyl group. Due to presence of this NO2 group, this methyl group is quite acidic. So in presence of this strong base, one proton from here can be abstracted. So this is acidic. Will attack to this carbonyl center. So one proton from here can be abstracted, leading to this anion. The OH will be oxidized as there is H available here. it will form this, to remove one of the OAT from the system. Understood? Let's go to the next question. So among the following, what is the correct statement? So this will be our P. Reaction. We have given this Grignard reaction and two product has been shown. So what is the correct statement? Let's read one by one. A is the major product and it will have 5 signals in proton decoupled 30. This is our P. 5 type of carbon. There will be 5 type of carbon. So A is the minor product and there is B and C, D are already cut. B is the major product. So correct option will be between one A or C. So let's do the next step. Now they have added zinc. Now we know that in presence of zinc, you need to get reduced to amine. Just try by yourself. In presence of zinc, you need to get reduced to amine. Will attack to the center. It may attack to the center, or another possibility is it can attack to this carbonyl center and open this one. So among these two attacks, this one is more favorable because of high electron. This is more electrophilic than that of the ester. More electrophilic than that of the other ester. So it will lead to the formation of 5-member ring. Then as that hydrogen is because the hydrogen is acidic, because this is at benzylic position, so this comes here and OH gets removed from the system. So the correct option is option C. Correct option is option C. Why this hydrogen got removed? Because it is a benzylic hydrogen, and always the benzylic hydrogens are prone to remove because of the stability of the carbon ion. Next is, so we know the use of PCC. PCC will undergo the oxidation. So it will undergo oxidation forming this. This up to this we all know. So A is our major product. A is our major product. Now what will happen in the next step? So A is our major product. From here you can see that okay, there is a proton. Here zinc bromide is just acting as a Lewis acid, and this going to attack here. Now the thing is, we have to concern about the stereochemistry. Here there is a methyl group which is already below the plane. So if you see the three-dimensional structure of this one, so if you add zinc Br2, it acting as a Lewis acid, so it controls the stereoselectivity of the reaction. So B minor with 8. And in presence of zinc Br2, now select. forms a coordination bond with this carbonyl oxygen, and the attacks become highly stereoselective. So as this is already above this space, compound becomes symmetrical. This attack becomes highly stereoselective. As this is already below the plane, specifically attacks from the above the plane makes a below alcohol. So the correct option will be option C. Just similar to this one. The difference is just here the methyl group is above the plane and their methyl group was below the plane. Okay, just similar to this one. So next is titanium containing reagents. The McMurray reaction is an organic reaction in which two ketone or aldehyde groups are coupled to form an alkene using titanium chloride compounds such as titanium chloride and a reducing agent. The reaction is named as a McMurray reaction. The McMurray reaction originally involved the use of mixture of titanium chloride and lithium aluminum hydride, which produces the active reagent. Related species have been developed involving the combination of titanium chloride or titanium tetrachloride or titanium trichloride with the various type of reducing agents like potassium, zinc or magnesium. Here I have shown the general pathway of the reaction, where this carbonyl, this titanium will attack to this carbonyl center and it will open up, and that will form a coordinate bond with titanium and forming this tricyclic ring. After that, this can also present as like this. So this undergoes a radical coupling. This undergoes a radical coupling, forming the coupling of two carbonyl compound, and further if we add proton into it, it will form an alcohol. And if you just add heat, it will give us an alkene compound. So what will happen if you add zinc tetrachloride and a titanium tetrachloride and zinc to this carbonyl compound? So this titanium will give one electron to this carbonyl compound and this will open up, and then two molecules of this carbonyl will couple to form this. So it will just reduce this keto. There is two types of probability. One, this H minus is coming from the below the plane, another is H minus is coming from the above the plane. So there will be two types of product is possible. One is above the plane OH and there is below the plane OH. But as this, if you just imagine this structure in a 3D molecule of this couple to form this transition state like this. These two 5-member rings, because both the H are below the plane. Both the H are below the plane. This part will be also same. I am not drawing it. After that, it undergoes, as they have given heat, reflux means they have given heat to it. Because of that, it will undergo the elimination of water, leading to the formation of a double bond between two molecules of this carbon. H minus will attack from the below the plane. H minus will approach from the below the plane. So H minus will approach from the below the plane, giving this as our product. Next step, we add LiNH4. What will happen? Okay. So there is one question which came in previous year GATE examination. So what will be the major product of this reaction? The correct option is in presence of. Okay. So one question came in previous year GATE examination. So there is a dialdehyde. So if you add titanium in, what will happen? The similar way, it will undergo the coupling reaction. Now the reaction, you have to see the reaction is at room temperature or at heating. So the reaction is at room temperature. So it will just stop here and undergoes a protonation to give us this dialcohol. Okay. So the main thing to notice about this reaction is that it will always give a cis alcohol. Always. Always a cis product. Okay. Let's go to the next topic, where we will discuss about reagents containing teen. Reagents containing teen. So trialkyl stanins can be added to a carbon-carbon double bond or triple bond, and this reaction is processed through a radical chain process. So if we add this teen reagent to a double bond, it undergoes a 1,2 addition. Similarly, if you add this to a triple alkyne, then it also undergoes a 1,2 addition, but the reaction through a trans addition. From the product, you can notice that when it is for a terminal alkyne, it undergoes through a trans addition of this teen and hydrogen but after to get a stability of the product, trans addition to give this cis alkene. Don't get confused by the trans addition and cis alkene. Here you can see I am talking about trans addition means the metal and the hydride is adding trans to this across this triple bond. Hydrogen is adding to the opposite side of the tin. So this is trans, they are adding through a trans, but the alkene is cis. This alkene is Z alkene. This alkene is Z. Now just to regain the stability of the it undergoes a rotation and it becomes a E alkene. But the addition, the hydride and the tin addition will be always across the triple bond. That is a trans addition. That is a trans addition, resulting a alkene which is called Z alkene, because the priority of the tin is higher than the hydrogen. Okay. So there are some application of this type of organostannine compound in carbon-carbon bond formation. The stereoselectivity of addition of aldehyde and ketone has been considerable interest. With benzaldehyde, the addition of 2-butanol stannine catalyzed by BF3 gives a syn isomer irrespective of the stereochemistry of the butanol group. So if you add this organostannine compound to aldehyde, it always give a syn isomer. That is, it always the newly formed carbonyl center and the previously presenting center in the alkene will always be seen to each other. It doesn't matter what is the stereochemistry of your stannine. What is the stereochemistry of your organostannine, that doesn't matter. It will always give a syn isomer in the product. So what will be the product in this case? I will just give 10 seconds. Just try to draw it by yourself. The hints I have already discussed. Just try to draw it by yourself. Here there is already a chiral center is present in one of your substrate. Here there is already a chiral center is present in one of your substrate. Now just by addition of this tin, there will be generation of 2 new chiral center. So what will be the stereochemistry of all the 3 chiral center? So let's try together. So here, as I have already told, it doesn't matter what is the stereochemistry of your organostannine. The newly generated 2 chiral center will be always seen to each other. So and this chiral center which is already present in the substrate, that is not involved in the reaction. So its chirality will be intact throughout the reaction. So this will be unaltered, whereas the newly generated 2 chiral center, that is this OH. So it will attack from this, side. Sorry. It will attack from this carbon. So it's forming this syn product in your system. Okay, let's go to the next one. So this will also give the same kind of product. Now when you add this acyl chloride into it, there is a OH, so this will be undergoes acetylation, and the other part will be same, just I'm not so this will be OAC. Okay. Okay, let's go to the next. So the structure of the intermediate A and the major product B formed in the following reaction are. So we have to determine what will be the structure of A and B. I just give 5 seconds try once. So if you add heat to this bialkyne type of compound, it undergoes a cyclization. So this comes undergoes a cyclization through a homolytic cleavage, forming two radical center. So this will be our A. Further, if you add this hydride donor reagent, that is Bu3SNH, so here instead of, you have to notice, okay, there instead of H they have added deuterium, so it will deuterium will be added into this compound, so the correct option will be option 1. Okay, so they just played, they instead of Bu3SNH they just added Bu3SND, so deuterium will be incorporated in your product, giving us B, this one. Okay, let's go to the next question. So what will be the products formed in the following reaction? So here I am just giving this as a homework because it's similar, I have already told tin can undergo a reduction through a radical pathway. So I am just giving this as one of your homework. Just try by yourself. If you are having any doubt, we will solve it in the next class and it will be clear. Okay. So the next topic we will discuss, that is lead containing reagent. So we have already discussed till now zinc containing reagents, titanium containing reagents, tin containing reagents. So next is lead containing reagents. Although lead tetraacetate may be employed for the oxidation of wide variety of organic compounds, its primary use is for oxidative cleavage of 1,2-diol. The oxidative cleavage of diol, particularly the vicinal diol, is an important organic reaction and has exclusively studied over the years. One of the most widely used reagents for the reaction is lead tetraacetate, and the reaction is also known as Krieg glycol oxidation, where this type of dialcohol undergoes oxidation and give us this, through cleavage of this carbon-carbon bond, give us these two carbonyl compound. To see the mechanism of this one, but it will undergo going through a cyclic transition state, where this OH will attack to this PV center and remove one of the OSC group, then another OH will attack to this PV center and remove another OH molecule. After that, so when forming this type of 5-member cyclic transition state, after that it undergoes again a bond cleavage, where this comes here, forming the two carbonyl compound, and lead diacetate gets removed from the system. If you add lead tetraacetate into this type of carboxylic compound, what happens? It undergoes a removal of this carboxylic group and give us this type of cyclobutane ring. If you see the mechanism, this PbOC whole 4 reacts with this acid, forming this complex. After that, after the removal of cleavage of this bond, it forms this RCOO dot, which further undergoes a carbon dioxide elimination through generation and generating this R radical, and this R radical again react with our PbOC whole size radical and forming this cationic species which react with any hydride source forming this hydrogenated compound. Most of these hydride source are, as a hydride source we usually use lithium aluminum hydride or NaBH4, lithium aluminum hydride or NaBH4 as a hydride source in this reaction. In the presence of lithium chloride, the product is the corresponding chloride. So if we add lithium chloride, after generation of this it forms this carbon plus, so this coordinate with our Cn minus and form this lithium from this chlorinated product. If you add a alpha hydroxylic carboxylic acid to this lead acetate, what will happen? So in the similar way, first this lead acetate will coordinate with the carboxylic group. After that, this alpha hydroxy undergoes a ring cleavage. So this comes here and it undergoes a bond cleavage, and through elimination of carbon dioxide it gives us this ketone as our product. So what will happen if you add to this carboxylic acid, if you add this lead acetate, what will happen? So if you see that it will undergoes a elimination of this carboxylic group, and there is a generation of a double bond. If you look into the mechanism, as we just let's go step by step. So what will happen first? This acid group will coordinate with this lead complex. After that, there is a proton which is very acidic, as it is a alpha proton. So this comes here, this goes here, and it forms this alkene product with the elimination of one molecule of carbon dioxide. And one molecule of PbOAC whole thrice. Okay. Let's go to the next question. So, if you add this lead tetraacetate to this carbonyl compound, what will happen? So it will just, let's go. So just try. I just give 1 minute. Just try. Try both of them. What will happen if we add lead tetraacetate to this carbonyl compound, cyclic carbonyl hexanone, and if we add lead tetraacetate to the same dicarboxylic acid, what will happen? Okay, so let's go step by step. So this can also present as a enol form. This can coordinate with our LTA. Forming this it undergoes a homolytic ring cleavage. Forming this O radical and PbOAC whole thrice radical. So it can also, so this O radical can attack to this OAC and it can also break this bond. Sorry. So O radical, this OAC can also get forming this OAC dot. Then this oxygen comes here and this bond can coordinate with this OAC, forming addition of OAC adjacent to the carbonyl. In this way we can instead of electrophile we can add a nucleophile just at the alpha position of the carbonyl. This is the advantage of this reaction. Understood? This is the advantage of this reaction. Usually by some other method like the enolate ester or something, we usually enter the electrophile at the alpha position of this carbonyl compound. But by this method we are adding a nucleophile. We are adding a nucleophile adjacent to the alpha position of the carbonyl compound. So what will happen in this case? Similar way, one of the carboxylic group will undergo coordination of this will undergo coordination with this lead tetraacetate. Finally it undergoes a elimination. This bond undergoes a cleavage. This comes here and this gets removed from the system, leading us formation of a cyclohexene. Formation of a cyclohexene. Okay, I hope it's clear. So is one of the question which is based on our previous topics. The most suitable reagent for the following transformation. What will be the more suitable reagent for the following? This is simple reduction of this alpha beta unsaturated double bond. So for the reduction of alpha beta unsaturated double bond, what we will use? We will usually use lithium and liquid ammonia. Okay. So this much for today's class. Thank you everyone. We will meet in the next class. Have a nice day. this question, they have asked for the major product form as X and Y. So we add LDA. There is a proton here which is acidic. So it will be taken up by LDA. A negative charge will generate here, that will attack to this selenium and fluorine will be removed. Again another molecule of LDA will be added and this will take another proton from here and that will attack to this methyl iodide and methyl will be inserted. So the first selenium will, as this is above the plane, as these two protons are above the plane, the first selenium will come from the below the plane and the next methyl will come from the above the plane. Next, if you add H2O2, this will be oxidized and selenium oxide will be formed, and this, as this proton is above the plane, so this proton will get removed and an alkene will form here. So you can see first selenium is coming from the above the plane, so the next methyl will come from the below the plane. If you add H2O2, the selenium will be oxidized, and here there is a two types of hydrogen, one is methyl and one other is proton. This one, as this is above the plane, in the same plane of the selenium, and after the deprotonation there will be a double bond which has some resonance stability, so this proton abstraction will be more favorable. So this will take up this proton and get removed from the system, generating a double bond here. So there will be a scene elimination. There will be a scene elimination. So what will be the product A and B in the following reaction sequence? So they have given this reaction and they have asked for the A and B. Just give it a try. I just give, this is a big one, so I just give 3 minutes. So let's see what will be the answer. So first, this TBAF will attack. TBAF is specially the gives a fluorine source F minus, and whenever there is a silicon and if you give a fluoride source, it will preferably attack to the silicon, because silicon fluorine bond is one of the strongest bond in nature. Silicon fluorine bond is one of the strongest organic bond in nature. Because of that, fluorine always prefers to attack to the silicon rather than any other places. So this fluorine minus will attack to the silicon, and I said that in the one of my classes I have already told, whenever there is an allyl silicon, it will attack to the silicon and this carbon silicon bond will break. So this carbon silicon bond will break and this will come here, and again this N will attack to this ester form moiety and it will be removed from the system, generating this as our product. So the correct A will be this one. So A will be this one. Okay. So as this double bond is migrating, so this is our correct option. The next step, if you keep heat, it seems like this is a diene and this is a dienophile. So there will be a 4+2 cycloaddition reaction generating this cyclohexane as our product. So the correct option is option A. Just note it down.